Okay, guys, we're on 6.4. Turn the page. Let me make this a little bit bigger because it's kind of small. There we go. Okay, so acid-base indicators are typically represented as HIN, IN for indicator, and then H just represents that it has a hydrogen attached to it. So this typically represents the acidic form of an indicator, okay? And over here, obviously, IN -1 would be the basic form, okay? And can I move down? Yes, okay. Let's take a look at an example. So bromethymol blue, which you probably used in biology. No?
Yeah.
Yes? Okay. The acidic form is yellow, and that generally occurs when the pH is below 6. We're going to be talking a lot about indicators here. And then the basic form is blue, and that's generally when the pH is above 7.6. And at the transition point, can I move? At the transition point, which is also known as the end point, the indicator will be halfway through its color change. So at the transition point, the concentration of the acidic form equals the concentration of the basic form. And in this case, the Ka will be equal to the hydronium ion concentration. Take a look at the next page. You take the negative log of both sides of the equation, the pKa of an indicator will equal the pH at the transition point. The things that I'm highlighting are basically the things that you should really know, okay? There is a table of acid-base indicators at the back of your book. It is table A6. You may want to find it and earmark that page. It will show you that the indicators change colors at different pHs, and those pH values are the pKa values for each indicator. Okay, and then let's take a look at the table. Did you find it in the back?
Yes.
Okay, perfect. Let's come down here. This gives you a great little summary. So when you see the indicator change colors initially, that's when the pH is equal to the pKa -1. And then at the transition point, that's when the pH is equal to the pKa. And then when the indicator is done changing colors, that's when the pH is equal to the pKa +1. So generally speaking, can I move down?
Yes.
Okay. Generally speaking, the pH range for an indicator in a titration is usually the pKa ±1. And then we normally choose an indicator whose pKa is within 1 unit of the pH at the equivalence point. And then an indicator's transition point pH and pKa can be estimated by averaging the two pH values with the range over which the indicator changes color. We're going to take a look at that on the next page. So let's turn the page. The table at the back of your book shows that an increase in pKa corresponds to a decrease in Ka. So that means the indicator acid strength decreases as you move down the table. Okay, similar to the strength of those Bronsted-Lowry acids and bases that we had looked at previously. The indicators that make up universal indicator, can I move this down? The indicators that make up universal indicator are provided for you right here. And they give you what the colors are, what the pKa values are. That's just kind of given as a reference. The one thing that I want to point out to you down here for this universal indicator is thymal blue. Where is my thymal blue? Okay, so there's an asterisk on thymal blue because it undergoes a color change over 2 different pH ranges. And the reason why is because thymal blue has got 2 hydrogen ions to give up. Okay, take a look at the next page. Let's take a look at the practice problems. Okay, practice problem number 1. The indicator bromphenol blue appears yellow at a pH below 3 and blue at a pH above 4.5. Estimate the pKa and Ka of the indicator and determine the color it will display at 1.8 times 10 to the negative 4th molarity. Okay, did you get something like that? Yeah.
Why can't you find the pH, like the concentration of H3O plus using the concentration of the HCl? Because if like HCl goes to like H plus and Cl minus, wouldn't the concentration just be that?
So, okay, on the previous page at the very bottom, when it says an indicator's transition point pH and pKa come from averaging the 2 pH values over which it changes color, I need to use that.
Okay, so
Does that, yeah,
okay.
yeah. Okay, any questions, other questions on that? Okay, how about number 2? If I want to estimate the hydronium ion concentration in this solution, and I have 2 different indicators, and they gave me the color, what could I deduce from this? pH. Okay, what about pH? Jules?
Right now, the pH for the cyst with the phenolphthalein, would it be less than 7?
Probably. You know that phenol red changes pH. Did they give you the pH range in that table?
Yeah.
What is it?
5.6.
That's when it starts changing?
Oh wait, that's methyl. Sorry. That's. Oh, sorry.
Is phenol red in there?
No. It's
No?
Yes. It says 6.6 to 8.0.
6.6 to 8. It's red. And then phenolphthalein is changing colors when?
8.2 to 10.
So you've got to be less than 8. Probably, or 8.2. Okay. So that means that, what could we say here?
Just take the average.
Take the average of the phenol red.
Wait, no, but that's when it changes.
So this is starting to change. Is it just flat out red? In the color change? Does it say it's just red? Does it say anything?
Yellow to red.
Yellow to red. Okay, so this is red. We are closer to the 8, I would say. Do you know what I mean? So therefore, we should probably deduce that the hydroxide ion concentration is probably slightly larger than the hydronium ion. Does that make sense? Okay. All right. Let's take a look at acid-base titration curves. Can I move on?
Yes.
Okay. Okay, this is where we're going to spend most of our time. And this is what most of your AP classroom stuff is on. Okay, that I had printed out and given to you. All right, so acid-base titration curves. So we've made titration curves, correct, in lab?
Yes.
Okay, so you're already relatively familiar with this. Let's take a look at the next page. And anytime you plot a strong acid with a strong base and you look at your titration curve, you're going to be starting at a relatively low pH. Your equivalence point is going to be around 7. Okay, and then you're going to eventually level off. And here in this curve, NaOH is added to HCl. And we know that because we're starting at the really low pH. Okay, if I was going the opposite direction, this would be inverted. Okay, all right, let's take a look at the next page. Okay, if I have a strong monoprotic acid and I'm titrating it with a strong base, then we will have a pH of 7 at the equivalence point because neither one of the ions that are from the salt can hydrolyze. So therefore the pH will not change and be slightly basic or slightly acidic. Okay, let's take a look at the next page. I'm going to talk about this ICF table in an example. Take a look at the reverse scenario here. Okay, here I'm still using NaOH and HCl. The only difference is that my pH is starting relatively high, and that's because here, what are we doing?
Adding HCl.
Yeah, so here we're adding HCl to NaOH. Okay, so it's just the reverse. My equivalence point is still at a pH of 7. And let's go to the practice problems on the next page. I'm going to stop this.